Hello and welcome to 3.3 Centripetal Force. So in the last lesson we looked at centripetal acceleration and we said that whenever something is going around in a circle that means it's accelerating towards the center. Well, for something to accelerate there needs to be a force acting on it, and we call that force the centripetal force, Fc, which is the net force that causes AC, the centripetal acceleration. And this force, it could be anything. It could be tension, it could be the normal force, it could be gravity, it could be some combination of those forces. The idea is that centripetal force can be caused by anything, but what it is a force that causes something to go around in a circle. So we can get that force from gravity or from tension, whatever it is. Okay, now one of the things that helps us get that sort of a force is a banked curve. So this is when we're driving along on the highway and there's a very sharp turn, sometimes the highway will actually be slanted. So if we're driving along here, here's my car, well, instead of the road being flat like this, the road might be sort of slanted like this to help me turn. And that's going to help me to get that centripetal force. And it's especially obvious on like a racetrack. So on a racetrack where you're going around this corner here, the corner is usually banked. So if you ever watch car racing. So a banked curve, this is a surface This is when a surface is on an angle to help something go around a curve. And the last problem we look at today is going to involve banked curves. Alright, so one last thing here. We want our equation for centripetal force. So that is Fc is equal to, well, mac. And that shouldn't be too surprising. F equals ma. Now remember, we have a few different ways we can write centripetal acceleration. So for instance, we could say this could be equal to m v squared over r. And remember that was using one of our definitions of centripetal acceleration, or we could say that it equals to, we could say here m times 4 pi squared r over t squared, or we could say that this is equal to m times 4 pi squared rf squared. And those are all sort of equivalent statements here. And so here I've just drawn a dot to mean times. Okay, so those are all equivalent statements. Down here we have a picture of an astronaut. He's just whirling a yo-yo around in a circle. And you can see that this astronaut isn't experiencing any gravity or anything, so the net force on this is just the tension. And you can see that that tension is causing our yo-yo to accelerate around in the circle. Perfect. Okay, we're going to deal with our first problem here. It says, suppose a bug is sitting on the edge of a horizontal DVD. The bug has a mass of 5 grams and the DVD has a radius of 6 centimeters. The DVD is spinning such that the bug travels around its circular path 3 times per second. So, in this picture here, this is our bug sitting on the edge of the DVD. The DVD is spinning around like this, and it's spinning so fast that it goes around in a full circle 3 times per second. Calculate the centripetal acceleration of the bug, the net force on the bug, and the force responsible for the centripetal force. Alright, so that's what we're going to do here. Step 1, centripetal acceleration. Well, we can get that here. We have our period. Actually, we have our frequency. Our frequency is 3 times per second. So here I can say AC is equal to 4 pi squared rf squared, and that's going to be 4 pi squared. Our radius is 6 centimeters. That is 0.06 meters. And that was r. And f is 3 times per second. Square that. This gives me 21.3 meters per second squared. Good. And since it asked for the centripetal acceleration as one of our answers, well, my final answer for that one is going to be 21 meters per second squared. All right, so that was centripetal acceleration. Now we want Fc. Well, this is equal to MAC. My mass here was 5 grams. So again, I'm going to put that in kilograms. That's 5 grams times 21.3 meters per second squared. And this gives us a force of 0.1066 newtons. Again, for our final answer, we want 2 digits, 0.11 newtons. So there's our 2 answers. The last one says, what's the force responsible for this centripetal force? So the question is, what is causing my bug to be accelerating towards the center of the DVD? Well, he's sitting on top of the DVD. Something's holding him on the DVD. It's not gravity, it's not the normal force. The thing that's keeping him on the DVD and pulling him towards the center is static friction. Otherwise he would just be falling off of the DVD. But static friction is holding him in place, so that is our force here. So we can say Fc is caused by static friction. And you can see again, our centripetal force could be caused by any number of things. Good. Next problem. We're going to calculate speed now. A roller coaster car is at the lowest point on its circular track. The radius of curvature is 22 meters. So we've got a roller coaster. So the roller coaster looks something like this maybe, and it's at some point here at the bottom of the roller coaster. We have this radius, so the roller coaster at this point looks like it's a circle, and it has a radius here of 22 meters. Perfect. Now we say the apparent weight of one of the passengers in the roller coaster is 3 times her true weight. Determine the speed of the roller coaster. So I'm going to draw a free body diagram, and this passenger is experiencing gravity. And remember, apparent weight. Apparent weight means how large is the normal force. So it says that the normal force up is equal to 3 times her true weight. So this is 3 Fg. Everybody see that? So we have 3 Fg acting upwards. And that's equal to the normal force. So that's what we're told here. We're told that the normal force is equal to 3 Fg. So what we want to find here is the net force. Remember, the net force on this car is what's causing it to accelerate upwards. So that's when I add up all the forces together, there's some net force. So I can say here that the net force is equal... Oh, I just lost my cursor for a second there. Okay, the net force is equal to, well, it's equal to the centripetal force. And this is equal to Fn upwards minus Fg downwards. Now I can fill some things out here. So Fn was 3 Fg, still minus Fg. So this is equal to 2 Fg, or I can say it's equal to 2 mg. There is our centripetal force. So now what I want to do is I want to find out how fast this roller coaster is going. So remember, I've got my equation here. Fc is equal to mv squared over r. We also said what Fc is equal to over here, so I can set that equal to 2 mg. And notice then Mass cancels out. We weren't given mass. When you're not given mass, well, you can usually assume that if you do the math right, that mass will disappear. So now I have this statement here, v squared over r is equal to 2g, which means that v is equal to the square root of 2gr, which is equal to the square root of 2 times 9.8 times 22 meters. And this gives me a v of 21 meters per second. There's my final answer. And again, I would have a therefore statement normally on that. But we're going to skip on to the next page. And this is the final problem I talked about at the start, where we're dealing with a banked curve. You can see we have a car going around this curve here, and the banking is going to help that car to make that turn. And we're going to see how that math works. Okay, this is a bit of a tricky problem as well, so we'll work through it. A car making a turn on a dry banked highway ramp is experiencing friction. And you can see that in the picture here. Static friction towards the center. Well, not exactly towards the center. It's perpendicular, or it's parallel to the surface here, which is always going to be the case with our friction. Okay, the coefficient of static friction between the tires and the road is 0.60. Determine the max speed at which the car can safely negotiate a turn of radius 2 times 10 to the 2 meters, with a banking angle of 20 degrees. So they tell us this is 20 degrees. They tell us that we are doing some circle here with a radius of 2.0 times 10 to the 2. That's just another way of saying 200 meters. And we've got the coefficient of friction. Okay, so how are we going to do this? I'm not even necessarily sure where I want to start. Well, this is about centripetal force, right? We've got some force that's pulling me inward. I can start by saying that the net force is equal to my centripetal force. The net force is what's causing me to go around in a circle. So this is equal to Fc. Now the net force is also equal to, and I can now take my free body diagram, which is already drawn for me. I don't even have to do that. That's nice. So I'm going to take my free body diagram and figure out some net force here. So let's see what we've got here. I'm going to say that I'm going to break up my forces here. Now remember I said break up your forces so that x is the direction of the acceleration. That's the easiest way to solve these problems. So in this case, I am accelerating not downwards. This is not the direction I'm accelerating. I'm accelerating in a circle in this direction, right? Even though the road is on this slope here, it's this direction that I'm going around in a circle. I'm not going down at all. I'm staying the same height on the road. So I'm just accelerating towards the center. So that means that this is my x direction. And I want to break this guy into x and y. And I want to break this guy into x and y. Okay, now I can do that. So you see I had 20 degrees here, which means that, using my knowledge of triangles, I can say, well, this is 20 degrees in here. And in here, this has to be 70 degrees, which is 90 minus 20. Okay, and so now I can do some components here. I can say that my net force, well, the vertical and the vertical has to cancel out, because I'm not accelerating up or down. So my net force is just these two horizontal pieces. Okay, so then I can say net force is equal to Fs cosine 20 degrees plus Fn cosine 70 degrees. Those are my two pieces. Okay, so we have our horizontal pieces sorted out. Now we're going to figure out the vertical piece and see if we can do something with that. So vertical pieces here have to cancel out to 0. So what I can say is the upwards piece here, we have Fn is this upwards piece. That has to equal to this plus this. They all have to cancel out. So I can say Fn times the sine of 70 degrees. Well, this is equal to Fs sine 20 degrees plus mg. Okay, so now we have a statement for that vertical piece. And since Fs is equal to mu s Fn, well, we can maybe clean this up just a bit. So I can say here that Fn sine 70 degrees equals mu Fn sine 20 degrees plus mg. And now if I combine these terms here, I can say Fn times this piece minus the piece from the right and this can give me a value for Fn then. So Fn is equal to mg over sine 70 degrees minus mu sine 20 degrees. Okay, there is a value that we can use for Fn. Up here we have an equation for Fc, and that's ultimately what we're going to use. So we can start putting some things together now, because we want to get the centripetal force, which will give us the centripetal acceleration, which will give us the speed, the maximum speed. And that's what we're trying to get at right now. So I'll go back to this statement here for Fc. I can say that Fc is equal to Fs cosine 20 plus Fn cosine 70. And I can just clean this up a bit by getting rid of Fs. Remember we said that Fs is mu Fn, and I'll just put in the rest here again. Okay, and now I can summarize this to say Fn times mu cosine 20 degrees plus cosine 70 degrees. Finally, I have a value for Fn. So I can say this is equal to mg over sine 70 degrees minus mu sine 20 degrees times now mu cosine 20 degrees plus cosine 70 degrees. And notice this is a lot. But now you can fill in your numbers for all of these, and we can get a value for Fc. So we can say that now Fc is equal to, I'm not going to put in the actual values, I'm just going to get us our final value for centripetal force. And I'm sorry, actually we can't do that. That would be too easy, because we don't have the mass. So we're still going to have to go a bit further here. So we have a statement for Fc. Now, Fc is also equal to mv squared over r. So if I rearrange this, I can say that v is equal to the square root of Fc r over m. And now you see that if I take Fc and divide by m, I'm going to get rid of that piece. So I can rewrite this whole thing here. So I have the square root of gr. You can see I'm multiplying Fc by r. So I take gr let's just do it like this here. GR, I've gotten rid of the m with this here. So we have GR over sine 70 minus mu sine 20 degrees times mu cosine 20 degrees plus cosine 70 degrees. And my goodness, this has been a lot of work for this problem. But finally we have now a way to calculate v. Again, I'm not going to plug in those numbers. The final answer we get is 49.17 meters per second, which we want to trim off to a nice 49. And then we would have our therefore statement, and we would say, hooray, we're done. That really, really challenging problem. That's one of the most difficult problems I think we'll ever look at in this class. So, congratulations, we made it to the end, and I will see you in the next lesson.